I want to introduce now constraint optimization, um, and, and let's look at the case of two variables first. So let's say we want to find the extremum, which means either the global max or min. So find the extremum of f of xy subject to the constraint g of xy is equal to 0. That is, we want to find the extremum of f of xy where xy satisfies this constraint equation, or where xy lies on the curve given by this equation. So notice that the constraint equation is going to be some curve on the xy plane, and we are evaluating the function f at points on this curve, and we want to determine the maximum and minimum of f on this curve. To do so, let's first recall something, that if let's say, so g of xy equal to 0, the graph of that is some curve in the plane. I'm calling that C, and recall that the gradient. So g of xy equal to 0, right? So this curve here is a contour curve of g. That is, this is a level curve of g of level 0. So we recall that the grade. So if I pick a point P on this level curve, then the gradient of g at P would be perpendicular to the curve. That is, it is perpendicular to the tangent vector at P. So the gradient vectors at points on a contour curve or a level curve are perpendicular to the contour. Okay, so let's now look at Lagrange multipliers. So again, remember, the goal is to optimize f of xy subject to the constraint equation g of xy equal to 0. Let's say that the extremum, that is the max or the min, let's say the extremum of f occurs at the point P satisfying this equation. So let's say P is the point on the graph of the constraint equation where the max or the min occurs. Then I claim that at this point, we already know that at this point, because this curve is the level curve of g, we know that at this point P, the gradient of g would be perpendicular to the curve. Now, since this is a curve, let's say that r of t is a vector function that parameterizes the curve. Then what I want to show is that if the extremum occurs at P, then the gradient of the function f at P will be perpendicular to the curve as well. Let's see why. So if the extremum occurs at P, then if I look at, so remember, r of t gives us varies over the points on the curve as t varies over the domain of this vector function. So f of r of t is f of r of t. If the extremum of f occurs at P, then f of r of t has an extremum at the point P, which, let's say, is equal to r of t naught for some t naught. Well, because f of r of t is a function of t, if it has an extremum at t naught, then the derivative of f of r of t with respect to t at t naught will be 0. That is, if f of r of t has an extremum at t naught, then then f of r of t has a critical point at t naught, that is, its derivative at t naught is 0. But by the chain rule, this is the gradient of f evaluated at r of t naught, dot product with r prime of t naught is equal to 0. Which means that the gradient of f at p, dot product with r prime of t naught is 0. So that tells us that the gradient of f at p is perpendicular to this curve. So then we see that the gradient of g at p is perpendicular to the curve at p. The gradient of f at p is also perpendicular to the curve at p. Therefore, the gradient of f at p is parallel to the gradient of g at p, and so the gradient of f at p is a scalar multiple of the gradient of g at p. So gradient of f at p is lambda times the gradient of g at p, and this lambda here is what we call Lagrange multiplier. Now, in my discussion here, the only assumptions that we require is that f and g are continuously differentiable in an open set containing the curve C. So let me recap what we have just said. If we are trying to optimize f of xy subject to the constraint that g of xy is 0, then if the extremum of f occurs at the point P satisfying the constraint equation, then P must also satisfy the equation that the gradient of f at P is equal to some scalar lambda times the gradient of g at P. So to find the extrema of f on the curve given by the constraint equation, what we need to solve is this system of equations that the gradient of f is equal to lambda times the gradient of g, where lambda is a scalar, and g of xy is equal to 0. Now the first equation here is equivalent to two equations, that is, partial of f with respect to x is equal to lambda times the partial of g with respect to x, and the partial of f with respect to y is equal to lambda times partial of g with respect to y. So the first two equations here is equivalent to the first equation in the first system. So to find the extrema, we basically have to solve this system of equations. Okay, so I'm going to stop here, and in the next video we will be looking at the case of three variables.